Welcome back, everybody. I welcome to this afternoon session. It will start with an invited lecture by Andras Schumann. The title of the presentation is Gamble Distribution, ARMA, Copulas, the Importance of Stochastic Tools for Water Management. Thank you. The floor is yours.
Thank you very much. Good afternoon, ladies and gentlemen. First of all, I changed the title because I expected that everybody is aware of the importance of stochastic tools in water management, and so I changed it. You can read it in the paper. You will find why I think it's very important. There's some evolution of the stochastic tools in hydrology in water management, but here I changed to problems in applying stochastic tools for water management. You see, I have a different perspective because I'm not a statistician. I come from the Water Management Commission. I represent here the Commission for Water Resources Systems of ICSH-IAHS, who was in some way a godparent of this commission, because we think it would be a very good idea to have an improvement of statistical tools we use in water management. And so I want to start with some problems in applying these statistical tools. I first of all want to differentiate between uncertainties. There are different ways to handle uncertainties and probabilities, and I would like to start with that. Then I have a look for flood statistics and climate change, social hydrology and statistics, and then I come hopefully in good time to the conclusions. First of all, we all handle here stochastic uncertainties, random processes. We start with the aleatoric uncertainties, that we have non-deterministic phenomena which can be quantified with standard probability theory. This is a basic assumptions we have here, but there's another uncertainty as well, the epistemic uncertainty, where we be aware that we have an incomplete knowledge about a phenomenon that affects our ability to describe it. And these are different assumptions to probabilities. Here at one side we have the probability that we can specify with the relative frequency of occurrence of a specific outcome, the frequentistic probability, and at the other side we have a statement of probabilities which is based on logical conclusions, which has some psychological components, experience, the degree of personal confidences. And it's interesting that the dominating concept of statistics in hydrology is related to the aleatoric probabilities, but the dominating concept of applications of statistics in water management is more related to the epistemic probabilities. And so we should make a difference between these two sides of probabilities, otherwise you will be disappointed that your aleatoric probabilities will not use by practitioners, and so we should be aware that there's a difference, and we should try to bridge the gap between these two probabilities in some way. To give you an example, let's start with flood statistics. You know that the first persons who has done flood statistics were not hydrologists, these were engineers, which were forced to estimate design floods. And there were some pragmatic approaches to use the highest observed flood plus a safety margin, a freeboard, then we have regional formulas. And the introduction of probabilities, the application of statistical tools started 70 years ago. And I can specify it quite well within the year 1941. And now we are in transition to risk-based design, where we understand that the uncertainties of uncertainties estimates is impossible, and we try to integrate more risk-based assumptions now in our flood design. Still in 1936, statistical methods in whatever form employed were seen as an entirely inadequate tool in the determination of flood frequencies, at least by Mr. Slade, who published this. But 5 years later, Gumbel please don't pronounce it Gumbel. It's German by origin, and I would prefer to express it as Gumbel. He published uncertainties. He published the paper Return Period of Flood Flows, and he mentions the preconditions: homogeneous series, common set of forces, independent of one another, and some of you mentioned it as ignorance of these unfulfilled preconditions, and I think it's really assumptions that we have, and we have to consider that this just is one assumption. Here you see an example, distribution functions of floods, and the question is this aleatoric or epistemic in the probabilities? I think we have here several parts. In this part, it's without doubt aleatoric, because we have here the statistics, we are in the range of our time series, but here at this side, if we go have a look for the tails of the distribution, we come in the range of epistemic components, because we have to decide what's the right distribution functions we use for the extrapolation, and this is not a question, or it could be a question, of course, of statistics if you believe in the goodness of fit tests and such things, but it has to do also a lot with epistemic components in statistics or the application of statistics. If we now look for the evolution of flood design, there's a transition from safety-oriented risk towards risk-oriented design. In the safety-oriented risk, we have a design flood, and we have the basic assumptions that no risk of failure exists if the discharge stays below the design flood, and that the risk would be negligible if because the design flood has a very low return period. If we look for the risk-oriented approach, you are aware that 100% safety cannot be reached by technical measures. That's a risk of failure anyway, combined from the hydrological risk, the operational and technical risk, and that risk management is required. These are different approaches. And to give you an example for that, here you see the inflow and the outflow from reservoirs. Here's the inflow and the outflow. And you see here in this, for this flood, we had nearly no flood protection. Here you would have the same flood, upper reservoir, you would have nearly a full flood protection, because the outflow is significantly smaller than the inflow. But there's also something between. In some cases, you could have in some time a good retention of the flood, but the second peak could not be retented at all. That means there are a risk that we cannot cover with our single design floods. That nature is much more complex, and flood protection by technical retention facilities depends on the characteristic of events we cannot consider up until now by these single design flood approaches. So it is insufficient to use design floods like this, to have such a Gumbel distribution of the inflow flood wave, and there you would end with a very comfortable relationship between the flood peak inflow and the water level in the reservoir. But this is just an assumption, and we cannot believe in that. And so there's a strong need to have more complex descriptions of the hydrological loads, which could be done, for example, combining different components of such a flood event, and to set up a stochastic generator of floods, which we have done here to simulate 10,000 inflowing floods and to estimate the most critical one. And it's interesting, if we would have a look for a more complex hydrograph, you would find that the flood is not defined by the return period. So the most critical flood is not defined by the return period of the flood peak. It's defined by the combination of the shape, of the volume, and of the flood peak, of course. And we are not completely wrong in our simulations here. You see the most critical flood for a certain reservoir in Germany, which was simulated by us. This is the blue line, and this flood happens in 2002, and it was the most critical flood ever we had at this single reservoir. You see, it's a need for multivariate statistical approaches, and so we are very satisfied by these copular approaches, which becomes more and more popular now. But what's the problem? Here you could, for example, set joint return periods of the flood peak and volume, and you could specify the design floods with these joint return periods quite easily. Here you see in practical application we have done in our consultancy work. Here you have two tributaries which are after the conferencing point relate to the flood risk of the city, and the question was where to build up a reservoir, in this tributary or in the other one. You have the marginal distributions, you have the correlations between the flood events of these two tributaries, and we could specify the change in the copular functions as it is shown here. If you would change the marginal distribution, you would end with upper return periods for the flood downstream. However, the problem is, are we able to specify the copular function in the right way? Here you see an example I've took from Andras et al. You see 1,000 random variables which are based from two distribution functions with identical gamma marginal distributions and identical correlations, but different in their dependence structure. And you see here that the interesting tails of the distributions show completely different performance. Here you see that you would have a high flood peak at both sides at the same moment. And here you see a wide range of different flood peaks if you would have a large flood here. The relationship of these, or the result of these differences, would be very important with regard to the flood management planning, because here you can be sure that you would reduce the flood risk after the conferencing point significantly by building a reservoir here or there. And here the changes would be much more complicated. The question is, can we specify the differences among these two copular functions in the right way? Here you see some data for this case study. These red triangles are the measured flood values of the two tributaries. And you see it's very, and the yellow points are simulated data from the assumption of the copular functions, and it's quite difficult to specify, is there an elliptic region or is these regions more, is there a divergence in the two flood peaks? You see, it's not that easy, as it has a high practical importance to specify the right model at the right for the right situation. And now I come to statistics and climate change. Here you see a typical trend. It's not caused by climate change as an assumption, that it's caused by urbanization. Here you see the yearly floods and an increase of the flood peaks. Is this really a trend? Or maybe these are breakpoints caused by changes of the location of the gauges, changes of the measurement equipment. Here you see 3 different periods. Each of them is stationary, whatever it means, but in total you get the impression that it could be a trend. I think this is a critical problem of our statistical assumptions. Here you see an example which is quite worse. You see the change of the river flood risk, which was published in 2010, and you see here the return period of nowadays 100 years flood in future. And you see that in some regions which are closely related, the 100 years flood would have a return period between 10 and 20 years, and close to it would have a return period of more than 100 years. I don't think that such studies are useful for us, because if you look for the large variability which we can expect in our statistical analysis. To give you an example, we had there a large flood in 2002 in Germany, and here you see the QQ plot of the distribution functions if you would not integrate this flood, which is located here, or if you would integrate this flood in probability distributions. And without the knowledge of this exceptional flood, we would assume that this flood peak would have a return period up to -4, not return period exceedance probability 10 up to -4. And nobody would say that we could expect such a flood, but if you would integrate this flood event into distribution functions, the return period will be reduced to 500 years or around 500 years. This shows that the natural variability is much higher than any pre-assumptions about the effects of climate change. And I think we should be careful with regard to our limited knowledge about past situations. This data I've got from Günter Blöschel. You see here the yearly flood peaks at one river basin, at one gauge in Austria, and you see this extreme flood event in 2002. But you see in the neighboring at the neighboring station, there were several of such events which were not considered in this short time scale, or in these short time series. And I think it's the most critical point here, that our knowledge is quite limited. I found a very helpful summary of the question of stationarity given by Linz and Cohn. And first of all, non-stationary axis is the first point, because the climate is changing and will change also in future. It's changing anyway. The other question is that stationarity and non-stationarity are essentially indistinguishable. And I think this is also very important, because we cannot be sure that we have stationary or non-stationary time series. It depends on the time scales. And last but not least, models results may be sensitive to arbitrary decisions regarding data and hypotheses. And the concept of statistical significance is meaningless when discussing poorly understood systems. And here you have the excellent example which was given by Dimitris, which is really a point in this direction, and I like this picture very much. Okay, I have done also some studies about climate change. We started with this in 1995, and we used their climate projections, which were provided by the University of East Anglia at that time. We used 7 different GCMs, which were based on epistemic uncertainty. Then we used 8 different ones of the Hadley model. We resulted in 14 different climate scenarios. Then we had different assumptions about global climate sensitivity. In that time we assumed that there would be an increase by 1.5 up to 4.5 degrees increase of global mean temperature. Then we had different emission scenarios, 4, which are known quite well, which are still valid. And last but not least, we added some natural climate variability, and we end up with 25,000 Monte Carlo simulations, and the result is shown here. It's a foreign watershed located in the upper Danube river basin, around 1,000 square kilometers. You see the change in the runoff in the winter half year and in the summer half year, and you see that the changes depend strongly from the model you use. It depends strongly from the assumptions of the modelers. This was published in 2001 in an IAHS conference in Maastricht, and it was the last publication I've done about climate change, because I thought it would not make sense anymore to use these climate models. But many other people have done this, spending billions of dollars. And for example, I met recently Gene Starkev, who spent $20 million using 23 global climate models for the Great Lakes, and they came out that there's a large uncertainty and he could not make any projections about future climate changes. And here you see a study which was done by one of my former PhD students, who is now at the Federal Institute for Hydrology in Germany, and he came to the same outcome we had nearly 15 years before, that there's a wide range of uncertainty in the precipitation, for example. And I think we should be careful that we don't use these ensembles of future climate predictions in a statistical way. The basic assumptions of all probabilistic approaches is that the ensemble should be statistical representative for the basic population of all possible states, and we cannot assume this for climate models. And even if we would not have 23 climate models, if we would have 230 climate models, they would also based on the same basic assumptions about relationships between climate and CO2 conditions and so on. And so we cannot make they would never have a probabilistic meaning from my point of view. Okay, what we should do is to be prepared for interactions, for potential surprises. There are many other driving forces for changes in water management: the interaction of population growth, increasing per capita water use, land use changes, pollution, loss of biodiversity, to mention just one of them. And we should make new strategies for these changes instead to look just for one component of changes, which is rather uncertain. And here I come to the questions of socio-hydrology and statistics. What means socio-hydrology? Water management handles the interactions of humans and water, and socio-hydrology, which was defined by Savenier and Shiva-Palan recently, is a study of the co-evolution of humans and water on the landscape. That means we have to consider a wider range of controls related to the interplay of socio-economic conditions than just in water management. And I think this is very important for future plannings or future developments in water sciences. To give you an example, here you see the declining of freshwater supply from reservoirs, and it was an interesting experience for these reservoir systems. I tried several times to improve the safety of the water supply from 95% to 97%, and I was successful to do this, but I ended this work in 86, and 14 years later the water demand was reduced by 50% because they introduced the new economic system of water pricing, and the water demand significantly was reduced by this new pricing system and some other changes of the economy. And here you see that there is a strong relationship, for example, for the costs of fresh water and the water demand per capita, which is shown by this regression, but it's not in every case. Here, this was the case of East Germany, where the water price was introduced, and you see in the western part of Germany no relationship between the increase of the water price in the water demand because the people are familiar with these prices and they don't shift their behavior in this direction. And you see it's much more complicated than just the statistical questions. Human behavior, it's very difficult to assume. Here you see an other example from our work. You see a water balance of an agricultural region in China, and they have a strong deficit in groundwater, which is difficult because this region is located closely to the seaside in northeast China. And the question was how to change the agricultural water use in future. We have the multi-dimensional problem. We could set up different changes in the crop types. We could bring in different types of irrigation. We have question of dimensioning, what steps of land use changes we should suggest, and we have unknown boundary conditions. Why farmers are growing these crops and not other crops? There's a question of the economical, social situation, cultural, historical situations, market developments, and we set up a stochastic land use change generator based on an analysis of existing trends in land use which happened in the last 50 years, and you see we set up these distribution functions, these are beta distributions, to estimate the decrease of crop area or the increase of crop area for more than 10 crop types. And we simulated then the different changes of these crops and estimated the change of the production and the change in water use. And we introduced the likelihood that people would really change the crops. And this likelihood is based on a distribution functions which has basic conditions that nobody want to do any changes, and that the people would not like to change very much their behavior. That we would have a greater chance if the people would stay in the comfortable situations that they have to do the same what they have ever done. But by doing this simulation, we found the range of feasible changes, which is located here. You see the yield, the water use, and in this part of our decision space, we can locate feasible measures where we would increase the economic income and would reduce the water use. And if you compare it with the actual situation, it's a very small range of possible changes. But you could estimate it if you consider that the people don't want to change too much and that you need some money to stimulate these changes. And so you see that also in social hydrology we could apply statistical tools in a much more complicated way than just to have a look at to natural variabilities, because it's related to the human behavior. Here you see changes in the irrigation, crop changes, and the level of acceptance. Of course, if you were to reduce income, the acceptance would be much lower than if you would increase the income. To come to the summary, statistics is a substantial component of modern water management. However, the application demands a quality management. What are the basic assumptions? What are the known unknowns? We should specify them. What are the meaning of probabilities for end users? Is there a need for interpreting the results? Can people differentiate between 97 and 99% probabilities, for example? What means should we know from deterministic components of hydrology? What are the relationships with deterministic components? How reliable are our statistical assumptions? Klemesh mentioned once, if we know the probabilities that a dog could increase, we could estimate the probabilities that a dog would be so large as an elephant. We could do that, but this would not really make sense, and so we have a maximum probable flood, for example, to consider, and other things. And I think all these basic assumptions are essential to avoid critical errors. It should not be such an error as it's shown here in this figure. Thank you very much for your attention.
Thank you very much, Andras. Thank you very much, Schumann. Thank you very much, Andras. Thank you very much, Schumann. Thank you very much, Andras. Thank you very much, Schumann. Thank you very much, Andras. Thank you very much, Schumann. Thank you very much, Andras. Thank you very much, Schumann. Thank you very much, Andras. Thank you very much, Schumann. Thank you very much, Andras. Thank you very much, Schumann. Thank you very much, Andras. Thank you very much, Schumann. Thank you very much, Andras. Thank you very much, Schumann. Thank you very much, Andras. Thank you very much, Schumann. Thank you very much, Andras. Thank you very much, Schumann. Thank you very much, Andras. Thank you very much, Schumann. Thank you very much, Andras. Thank
Thank you, Andreas, for the nice presentation. I think we have some time for some questions. So please, questions? Dimitris? I don't have a microphone.
Here it comes. Like your entire setting and the philosophical issues that you mentioned. So I wanted to ask a question. You mentioned the comparison of 23 models by 23. By Starship. Yeah. And you mentioned something about some several millions of dollars or euros.
Yeah.
So let's assume that we have two competing groups. One asks several million dollars to make such a study about the impacts of climate change using fourth, fifth generation climate models. And on the other hand, we have another group which promises the same thing using statistical methods, common sense, etc. I believe the results would be more or less the same. Who you think will get the job?
Of course, the modelers. Of course, the modelers. Because it's a never-ending story. Yeah.
Yeah.
Thank you for this comment. Other comments? Questions? Okay.
You said that the tail of the distribution is dominated by the epistemic uncertainty and probability. And I didn't understand. It's interesting. What is the reasoning behind?
I think I would like to use this figure to explain that. You see, I show this distribution very often to my students. Here you see that thank you very much. You see that the distributions, different distributions, there are several of them, are closely together in the range of known data. Up to 50 years, there are not really a difference. In the extrapolation, you have large differences, and here you have sparse data, you have nearly no data, you have 2 or 3 events. And you have to specify now what's the right distribution. If you would assume that the reasons for this plot would be different, that this is a non-homogeneous sample, which is quite, I think you should expect that. You would be completely misled by this good representation of the known data or the known range of information.
So the big range of the models you call epistemic uncertainty.
I think it's epistemic because you have to decide which one of these distribution functions you use based on these information, which are not too different. You see, if you have these informations available, which are nearly the same, you have not really significant differences, but you are looking for the upper tails. And here, the information are very scarce, and it depends what you expect, what would be the probabilities of these floods. And if your time series would be longer, the probabilities would be shifted to the right directions, I suppose. In most cases, we have this problem. And so it's if I'm a water manager, I have to decide what type of distribution I trust. There are some basic approaches that should be a similar distribution in the same region, or you have here this presentation from the lady from Poland. We have some space for new distribution, which would be different here in this range, but quite similar in this range. There are a lot of uncertainties related with that. And if you would say, okay, we have these good methods to test the goodness of fit, it's also an assumption that you can use these tests, yes? You cannot be sure that the basic assumptions is true.
There's just one last question I would say from here.
Socio-hydrology concept. So there is interaction between society and hydrology. So we are hydrologists. My question is that should we look at the society to find our way, or should society look at us to find its way? What's your opinion about that?
We have, of course, society should look for us I think everybody is expecting that I answer in this way, but I'm not sure about this. And I started in my professional career as a water manager. I was 8 years water manager in a large water management board. I was responsible for practical water management. And now I am doing a lot of consultancy work for the World Bank and water management authorities in Germany. And every time I have to translate hydrology into socioeconomic conditions, because the people are not interested what's the difference in the distribution functions. They are interested in the outcome, in the costs of levies and such things. Yes, and so I think we should be aware of this, and we should be also try to moderate our outcomes or to adapt it to the expectations of the society in some way. We cannot wait that the society expected will understand it completely, directly.
But I believe by definition, hydrology is socio-hydrology.
It is.
Because it serves some needs of humans, of the societies. And also, if you see the definition, it says, in 1960s, you will see that it includes in the definition the interaction with humans. So, from whichever point of view you see a hydrology, it is socio-hydrology. So I wonder if we need the term like socio-hydrology, because hydrology, I think, is sufficient.
It has it directs our emphasis a little bit more to these questions. I think this is the best way.
Because perhaps we have departed from the real world and
in some way.
Okay. Thanks to everybody for the very interesting discussion. Since we want to keep the schedule, I would think we can move forward to the next session. I believe there's no coffee break at this point. No coffee break, so we move straight to the session 3, reservoir management, multivariate flood statistic and its practical use, that will be chaired by Alberto Montanaro.